Next we have reflection and refraction on the basis of Huygens principle. The laws of refraction on the basis of Huygens principle. That is, we are using the Huygens principle for the refraction and reflection. So first we have plane wavefront refracted in the rarer medium. Consider a plane wavefront, that is AB. This AB is a plane wavefront incident at the interface of XY. XY is an interface which is separating the medium 1 and medium 2. Let N1 be the refractive index of first media and N2 be the refractive index of second media. Here the N2 is less than N1. So it says that N1 forms a rarer media and N2 forms a denser medium. Let the wavefront reach from B to C. See, the wavefront reaches from B to C in the time t with the velocity v1. So we have the length BC is equal to v1 t. So let the velocity of the wavefront from A in the rarer medium be v2. The velocity at the point of A, it will be the v2, and then in the time t, distance covered will be, the distance covered by this wave will be, that is AD, that is equal to v2 t. So by using these two, we have BC divided by AD is equal to v1 divided by v2. So by the triangle ACB, we will get BC is equal to AC into sin I, and next is triangle ACD, we have AD is equal to AC sin R. So by these two equations, we will get sin I divided by sin R, that is equal to BC divided by AD. We know that BC divided by AD is equal to V1 divided by V2. So for this V1 divided by V2, multiply and dividing by C, that is the velocity of light in the vacuum. So we get C divided by V2 into V1 divided by C. So we know that C divided by V2, that is the absolute refractive index of medium 2, that is N2, that is C divided by V2 is equal to N2 we have, and V1 divided by C, that is the 1 by N1, that is the refractive index of first media with respect to the vacuum, that is absolute refractive index of N1. So we will get the V1 divided by V2 as the N2 divided by N1. So we have sin I divided by sin R is equal to N2 by N1, that is equal to N1 sin I is equal to N2 sin R, which is the Snell's law of refraction. Hence it is proved. Next we have laws of reflection on the basis of Huygens principle. In case of a reflection we are seeing. So consider a reflecting surface XY on which the plane wavefront AB is incident at a point A. This AB point incidents at the point A. According to the Huygens principle, each point on the incident wavefront AB acts as a source of new disturbance or a secondary wavefronts. So if v is the speed of a wave and t is the time taken by the wavefront to reach the from C to B, then the disturbance or the distance is equal to, we will have the distance BC is equal to V into T. So now draw a sphere of a radius BC from the point A. We are drawing a sphere of a radius BC, that is V into T, from the point A. And next draw the tangent to this plane. We are drawing the tangents. See here, this line, this red line indicates the tangent drawn at the one point of that sphere. So we get that. Then we have that AD is equal to BC is equal to V into T. This, the length AD is equal to the length BC, that is equal to VT. We know that by this equation. So the triangles DAC and BAC are congruent and right angled. So in the triangle BAC, we are having BC is equal to AC sin I and in the triangle DAC we are having AD is equal to AC sin R. So by using these two we can say that AB is equal to BC. We know that AB is equal to BC. So by using these our equations we have that, sorry, it must be AD here. AD is equal to BC. By this equation we know that AD is equal to BC. So this we are substituting these two equations in the above equation. That is will become AC sin I is equal to AC sin R. So here we have AC, so that will get cancelled. So we can write that I is equal to R. Hence the law of refraction stating that the angle of incidence I is equal to the angle of refraction R is proved. Hence we have proved the laws of reflection and refraction on the basis of Huygens principle. Next we have a coherent and incoherent addition of light. To have a proper knowledge about coherent and incoherent addition of light, we are studying a principle, that is the superposition principle. What it says, let's see. This principle can be stated for two or more waves superimposing upon one another, resulting into a new wave which has a resultant displacement at any instant equal to vector sum of the displacements due to individual waves at that instant. That is, if we are having two or more waves and we want a resultant wave out of that two or more waves, so the superposition principle takes their means it is based on the the phase difference. Because of that phase difference there will be the addition or a subtraction of the waves takes place and we will get a resultant wave here. So that will be the y is equal to, that is the resultant wave is equal to y1 plus or minus y2 plus or minus y3, where y is a resultant displacement and y1, y2, y3 are the individual displacements of superimposing waves. So here we have two types of superpositions, that is constructive superposition and a destructive superposition. In constructive superposition what happens, if y1 and y2 are the two individual wavefronts or waves, then there will be after addition of that waves or the resultant wave of that two waves will be the addition of that two, that is y is equal to y1 plus y2. This happens only when the two waves are having the same wavelengths. They must be having a same wavelengths, so that, see here in the diagram A we are seeing the crest of one wave falls over a crest of another and trough of one wave falls over a trough of another wave. So by these two we can say that there is a constructive interference, constructive superposition takes place. So because of constructive, the resultant wave will be the addition of that amplitude of the first and second waves. So these black lines indicates the wavelengths or amplitude of the first and second waves, and the resultant will be the addition of these two, that is the red line. So in constructive superposition we can say that the resultant amplitude of the wave is increased, and we have another one, that is destructive superposition. In this the two waves of us doesn't have a same wavelength, or the trough of a in case of a destructive superposition, when the waves of same wavelengths superimpose on each other, that is in the out of phase, that is the crest of one of the wave falls on a trough of another wave, but they forms a destructive superposition. That is, the y1 is having a different wavelength or amplitude, and y2 is having a different amplitude, but whatever the resultant will be, that is the difference between those two. That is, we can write as y is equal to y1 plus minus y2, because of they are superimposing in out of phase. So that's why we will get a destructive superposition. And in this case, whatever the resultant wave will be, that it will be in that there will be a decrease in the amplitude or a intensity. Next we have coherent sources of light. Coherent sources means the two sources of a light are said to be coherent if they emit the waves of a same frequency or a same wavelength and are either in phase or have a constant initial phase difference. Those type of sources are known as a coherent sources. So by this diagram we can see this is the parent source. From this parent source we are getting the two coherent sources. That is, we have divided that source by using the two slits S1 and S2, and we are getting the two another sources which are having having the same frequency or a wavelength, and they are having the in phase or a constant initial phase difference, so that we can say that S1 and S2 are the coherent sources. Incoherent sources means the sources having the different frequencies or a sources having same frequency but no stable phase difference are known as incoherent sources. See, we are using here lamp 1 and lamp 2. We are using the two sources. Because of these two sources, they might be having the different frequency or a different intensity, so or there may be they are having the difference in the phase differences also. These are called as incoherent sources of light. Next we have interference of light and Young's experiment. Interference means, see, the phenomena of distribution of light energy due to the superposition of light waves from two coherent sources is known as the interference of light. We have the examples of interference as see when in a highway roads we can see when oil spills out of any tanks or what, the road from that oil we can see the lights coming out of that. So colored marks, colored streaks are formed due to the interference of light reflected from that oil. That is one type of interference. And similarly, when a soap bubble appears colored in sunlight, if we take a soap bubble and we see it in a sunlight, we will get to see that the multicolors in that soap bubble. That is also one of the example of a interference. So the relationship between the phase difference and the path difference is, if the path difference of any two waves is lambda and the phase difference between that two waves is known as 2 pi, then the path difference between two waves is delta x. Sorry, it must be not the path difference between two waves. The wavelength of two waves is lambda and the phase difference between them is 2 pi, and the path difference between them, that two waves, is delta x. Then the phase difference we are having as phi is equal to 2 pi by lambda into delta x. That is, here the 2 pi is the phase difference between them, lambda is the wavelength, and delta x is the path difference. And this is the relationship between phase difference and the path difference. because of the constructive superpositions and destructive superpositions, we have the constructive interference and destructive interference. In constructive interference, the waves, whatever we are taking, two or more waves, they will add, and whatever the resultant will be there, that will be of a higher intensity. And in case of a destructive, when we add the two or more waves, because they add in out of phase, so that's why whatever the output intensity or resultant intensity will be, that will be in a reduced one. So the conditions for constructive and destructive interferences are, see, the constructive interference occurs when the amplitude and hence the resultant intensity is maximum. So the constructive interference takes place if the phase differences between two superimposing waves are an integral multiple of 2 pi. When the constructive interference takes place, that is only when the phase difference between the two superimposing waves, that is the integral multiple of 2 pi, that we will get as m. Path difference is equal to wavelength divided by 2 pi into phase difference. Therefore, the path difference for a constructive interference will be delta x is equal to lambda divided by 2 pi into 2 pi m, because it is a integral multiple of 2 pi. So, we will get a m lambda, where m is the integral values, that may be 0, 1, 2, 3 and so on. And the intensity will be maximum at those points on the screen where path difference between the two interfering waves is an integral multiple of wavelength lambda. And this is the condition for a constructive interference. And in case of a destructive interference, the destructive interference takes place if the phase difference between the two interfering waves is an odd integral multiple of pi. That is, path difference is equal to wavelength divided by 2 pi into phase difference. We are having this formula. So, the path difference for a destructive interference will be delta x is equal to lambda divided by 2 pi into, it is an odd integral multiple. So, m plus 1 by 2 into 2 pi. We are having, so that's equal to m plus 1 by 2 into lambda. And this gives the destructive interference. And this shows the variation of the intensity of light with phase difference in interference of light. Next we have a Young's double slit experiment. This is the important one. The Young's double slit experiment was demonstrated by the Thomson Young in the year of 1801 to 1802. The experimental setup and working, we will see. The Thomson Young allowed a light to fall on a fine narrow slit S. The light waves from a S spreads out in all the directions. See, he had made to fall the light on a fine narrow slit. See in this slit S. Next, that light waves from that slit S spreads out in all the direction. After coming through that slit, the light will spread out in all the directions. So these waves were made to fall on two very fine slits S1 and S2. Whatever the waves coming from this S slit, they are made to fall it on another two fine slits S1 and S2, which are parallel and very close to each other. See in this, the light source is made to fall on a slit S, and after from this slit S, again whatever the light rays comes out of this S, he had made to fall it on a S1 and S2 slits, which are parallel to each other and very close to each other. and S1 and S2 were equidistant from S. From the S, the S1 and S2 are at the equidistance, that is they are placed at an equal distance. Next, the S1 and S2 slits gives the waves same wavelengths and nearly same amplitudes. These S1 and S2 waves will give the waves which are having the same wavelengths and nearly same amplitudes. These waves were superimposed on each other and give rise to the interference of light, and this will give the alternate dark and bright fringes or bright bands were obtained on the screen placed at the certain distance from the plane S1 and S2. And this is the a little bit construction and working of the Young's double slit. He had made to fall on a light from slit S to S1 and S2 because he wants to get a coherent light source, or when the light comes from the slit S, this will be in a coherence, so he had used S1 and S2. See, when we get a patterns on the screen, that is the dark bands are represented by the capital D's, and while the bright bands are represented by the B's. So see, this is the when the plane wavefront lights are coming to the slit S, after passing through the S, we will get a light rays which are traveling in all the directions. So when this light is made to fall on a S1 and S2 slit, so we will have a two more lights or light waves we will get from S1 and S2, and these two are made to superimpose on one another to get a bright and a dark fringes, that is see here, and this center O will be the central maxima because this is the mixture of both the slits. So we will get a central maxima at the point O, and next alternatively we will get the dark fringe, bright fringe, dark fringe on either side. See here, dark fringe, bright fringe, dark fringe. Wherever we have a dark fringes, that shows the destructive interference, and wherever we have a bright fringes, then these dots, that will represent the constructive interference. Now we see the derivation part of this, that is the theory of fringes, at which length we will have a bright fringe, at which length we will have a dark fringe. We will see that one. Dark and the bright bands in the interference patterns are called as interferent fringes. Whatever the bands we are getting from this Young's double slit, that we are calling it as a interference fringes. See, consider here the coherent sources S1 and S2, this S1 and S2, and separated by the distance D. So let capital D be the distance between the screen and the plane of slits. See, from this to this we have a distance D. Next, the light waves emitted from the S1 and S2 reaches the point O on the screen after traveling the equal distance. From S to S2, S1 and S2, there is a same distance for the point O, so they will travel the same equidistance to get a point, to meet at the point O. So path difference and the phase difference between these two waves is 0. So as they have moved in a equal distance in a equal time, so there is a no path difference and a phase difference. So therefore they meet at a point O in phase, and hence a constructive interference takes place at a point O. So at this point O we will get a central bright fringe. that is the maximum intensity light we are getting. So we are denoting it as a central bright fringe. Next, let the waves emitted by S1 and S2 meet at a point P. This S1 and S2 meet at a point P on the screen at a distance y from the central bright fringe. This length OP is a y. The path difference between these waves at a P is given by, see here, by seeing also we can say the S1 has moved less distance and S2 have moved more distance. So there is a path difference, right? So we will have a path difference as delta x is equal to S2p minus S1p, because S2 slit have moved at a larger distance. So we are having S2p minus S1p. So by using a right angle triangle S2BP, S2BP, see, it is a right angle triangle. By using this right angle triangle, we are having S2P is equal to S2B square plus PB square raised to 1 by 2. So that will be, we are having S2B is the D square, and next we have PB square, that is y plus D by 2. See, these are the lengths. This whole length A to B is called as a D. So from central to A and central to B, we are having D by 2. So from P to O we are having Y. From O to B we are having D by 2. So the total length from P to B we will having Y plus D by 2. So we will get this 2P is equal to D square plus Y plus D by 2 square whole raised to 1 by 2. That is equal to, we are taking the D as a common here. So we will have D into 1 plus Y plus D by 2 square divided by D square whole raised to 1 by 2. Next, by using a binomial theorem and neglecting the terms containing higher powers. In this equation, we are using a binomial theorem and we are neglecting the higher order terms. So we will get the S2P is equal to D into 1 plus Y plus D by 2 square divided by 2D square. So we can write S2P is equal to D plus Y plus D by 2 square divided by 2D. This is for a S2P. And similarly for a right angle triangle S1AP, we will have S1P is equal to D plus Y minus D by 2 whole square divided by 2D. Substituting these two values S2P and S1P in the equation delta x, we will get delta x is equal to 2YD divided by 2D, that is equal to delta x is equal to YD divided by D, where small d is the distance between slit 1 and slit 2 and capital D is the distance between slits to the screen. This is the total path difference between the waves at a point P. And next, for a bright fringes, that is the constructive interference, we are having, see, if the path difference is an integral multiple of lambda. We know that to get a constructive interference, we have to get a path difference that is the integral multiple of lambda. Next, then the bright fringe will be formed at a point P. See, at point P, there is a bright fringes. So that is YD divided by D. Here we have calculated the point P. So YD divided by D is equal to M lambda, or we can write Y is equal to M lambda D divided by D, which is the position of a mth bright fringe from the central bright fringe. So by substituting the M as integral values, we can get the first, second, third bright fringes. That is, for M is equal to 1, we will have a y1 is equal to lambda d divided by d. This is the first bright fringe from the central bright maxima. And for m is equal to 2, we will have a y2 is equal to 2 lambda d divided by d. And up to for mth terms, we are having the y is equal to m lambda d divided by d. This is the position of a bright fringes. Next we have a fringe width. Fringe width means the distance between any two successive bright fringes or a successive dark fringes. Now we are having the fringe width means the distance between two successive bright fringes. Here we have calculated for a bright fringes, and y1 is a bright fringe, y2 is a bright fringe. So that this difference between those two we will get as a distance between the bright fringes, that is the fringe width. So that is denoted by the letter beta, that is equal to y2 minus y1, and we are having the y2 as a 2 lambda d divided by d minus y1 as a lambda d divided by d. So by these equations we will have a beta is equal to lambda d divided by d. This is the fringe width. Next we will see for a dark fringes, that is for a destructive interference. By virtue of a destructive interference only we are getting the dark fringes on the screen. So to get a dark fringes, that is for a destructive interference, we have seen that the path difference must be the odd multiple of lambda. Then the dark fringes is obtained at a point P. Consider. So we will have yd divided by d, that is for a point P we are having the path difference as yd divided by d. So that will be m plus 1 by 2 into lambda. So we can write y is equal to m plus 1 by 2 lambda d divided by d, which is the position of a mth dark fringe from a central bright fringe. So on substituting the m values or a 0, 1, 2, 3, we will get the position of a dark fringes. That is for m is equal to 0, the first dark fringe will be obtained, that is for y0 is equal to lambda d divided by 2d. So next for m is equal to 1, we will get the dark fringes at y1 is equal to 3 lambda d divided by 2d. So next we will find the fringe width, that is for a dark fringe width, that is the distance between any two successive dark fringes. We know that y0 is a first dark fringe, y1 is a second dark fringe. So beta, that is the dark fringe width beta is equal to y1 minus y0. So we have y1 as a 3 lambda d divided by 2d minus y0 as a lambda d divided by 2d. So we will get beta value is equal to lambda d divided by d. And these equations, by seeing these all equations, we can see that the fringe width of a bright and a dark fringes are equal. See, beta is equal to lambda d divided by d, and for a dark fringe, the bright fringe we got beta is equal to lambda d divided by d. So the fringe width for a both dark and a bright fringes are equal. This is regarding the Young's double slit experiment. Next we have a diffraction of light. Diffraction means this is a phenomena of a bending of light around the edges of a obstacle or a corners of a obstacle or an aperture into the region of geometrical shadow of an obstacle is known as a diffraction of light. Or simply we can say that the diffraction of light means the bending up of a light around the edges of an obstacle. See, the AB is a obstacle here and the S means it is a source of a light. So when the light comes and hits at a point A, it bends around this edge, and at a point B also the light goes bending at the edge of that obstacle. So we will see this as a diffraction of light. There are two types of diffractions, that is the Fresnel's diffraction and a Fraunhofer's diffraction. Fresnel's diffraction means in this type of a diffraction, the source of a screen or source or the screen are both at a finite distances. If we place the source of light and a screen where we will get a fringes or a bands, that is both are kept at a finite distances, and that time whatever the diffraction occurs or a diffraction patterns we will get, that is known as a Fresnel's diffraction. And see this equation, this diagram A, this is for a Fresnel's diffraction. And next for a Fraunhofer diffraction. In Fraunhofer diffraction, the source and the screen are at a infinite distances, and that time whatever the diffraction pattern we will get, that time that is known as a Fraunhofer diffraction. And to get that diffraction pattern, we are using the convex lens here to make the rays to converge at a certain distance, and we have to get that pattern. So we have used here a convex lens in case of a Fraunhofer diffraction, and this figure B shows this is for a Fraunhofer diffraction. Next we have a diffraction of light due to single slit. As we have used in the Young's double slit, we have used two slits there, but now we are using a single slit and we are studying the diffraction pattern. A diverging light from a monochromatic source S is made parallel after refraction through the convex lens. We wanted a parallel source of light, so we have used here a convex lens, and then it made as a parallel lines or parallel rays of light, and after reflecting through the lens L1. So, and this plane wavefronts W dash are made to fall on a slit AB, and it is a very small slit, very small opening, that is AB. It is having the width D. See here in this we are denoting D as a width of the slit. So according to Huygens principle, each point of a slit AB acts as a source of secondary disturbance or a wavelengths. So the convex lens L2 helps in converging the parallel beam. Here after diffraction taking place at a point A and B, whatever the rays coming that are made to converge by using a lens L2. Now consider a point O on a screen. See point O, which is placed at a distance D from the slit. The distance between the screen and the slit is taken as a capital D. Since the point O is equidistant from a point A and B, this point is equidistant from the point A and from point B. So there is the secondary wavelengths from A and B reach the point O in the same phase, and hence constructive interference takes place at a point O. Hence they have crossed a equal distance, so there is no any path difference. So there is a constructive interference takes place at a point O. So we will get a central maximum at point O. Next, now let a light be diffracted through some angle theta. We are having a angle theta here, diffracting angle. So the secondary wavelets will also be diffracted through some angle theta. So let these wavelets meet the screen at a point P. When the diffraction takes place at a point theta, we will get a point P on the screen, and this point will be maximum or a minimum intensity depending on the path difference between the secondary wavelets, that is whatever the rays coming from the point A and B. If they are having a constructive interference, then at that time this point P will be the bright fringe or it may be a dark one. So now we'll see the path difference. Path difference, to find out the path difference between the secondary wavelets originating corresponding to point A and B of a plane wavefront, draw AN perpendicular on BB dash. We are drawing a AN perpendicular on the line B dash. So the path difference between these wavelets originating from A and B is Bn. This Bn is a extra path covered by the rays coming from point B. So we will have from BAN triangle, we will have Bn by AB is equal to sin theta, Bn by AB is equal to sin theta, or we will have Bn is equal to AB sin theta. Therefore Bn is a path difference here, it is an extra path covered by that ray. So here Bn is the path difference, so Bn is equal to d sin theta, and we can write it as, where theta is very small, so we can write it as d sin theta is equal to d theta. Let path difference be equal to the one wavelength, that is Bn is equal to d sin theta, that is equal to lambda. Consider it as a Bn is equal to d sin theta, that is equal to lambda. Then divide the slit into two equal halves. Divide the slit into two equal halves, that is AC by CB. AC and CB. We have divided the slit into two equal parts. Now the path difference between the secondary wavelets originating from A and C is equal to lambda by 2. This point and this point, that may be the difference, path difference originating from that point A and C be lambda by 2. As we have considered from A to B as a lambda, so half of that it will be lambda by 2. So these wavelets will meet at a point P with out of phase. So hence there is a destructive interference. So we will get as a position P with the minimum intensity. So first minimum we are getting as a d sin theta 1 is equal to lambda, or a sin theta 1 is equal to lambda by d. So theta 1 is a lambda by t, where we have taken theta 1 as a very small. So if similarly, and this theta 1 is for a angle for a first minimum, and if we have taken Bn is equal to 2 lambda, this Bn is equal to 2 lambda. So then the slit AB can be imagined to be divided into 4 equal halves. Then the path difference between the secondary wavelets originating from the corresponding points of each half, that will be lambda by 2. We have Bn as a 2 lambda, and if we imagine that AB is divided into 4 equal halves, so one of the half will be lambda by 2. So thus these wavelets produce a destructive interference, and at a point P we will get a minimum intensity. So secondary minimum we will get as a d theta 2 is equal to 2 lambda. So sin theta 2 is equal to 2 lambda divided by d, or where theta is very small, so we can write it as a theta 2 is equal to 2 lambda divided by d. By these two equations, in generally we can write as a the theta value or angle for a minimum intensity we are having as a theta m is equal to m lambda divided by d. See, at for a first angle we will have 1 lambda divided by d. For a second one we have 2 lambda divided by d. So in general we can write it as a the angle for a minimum intensity as a theta m is equal to m lambda divided by d. This is with respect to minimas. Next, for a secondary maximas, see, if the path difference bn is equal to d sin theta is an odd multiple of lambda by 2. In this we have taken as a integral multiple. Now we will take as a odd multiple of lambda by 2. Then the constructive interference takes place. Hence, the point P is the position of secondary maxima. At this point, P acts as a secondary maxima. So, that time we will get as a d sin theta m is equal to m plus 1 by 2 lambda. Or we can say sin theta m is equal to m plus 1 by 2 lambda divided by d, where theta m is a very small. So sin theta m is equal to theta m. So we can write in generally as a theta m is equal to m plus 1 by 2 lambda divided by d. That theta m gives the angle giving the direction of a mth order of a secondary maximum, where m is from 1 to n. And this was with respect to secondary maximum. Next we have a central maximum or a principal maximum. This point, that O, initially it was a central maximum. Now we have changed the angle theta. So where the central maximum will be? Now we will see that one. That is, the central maximum occurs at a O on the screen, at point O. So where angle theta is 0. When angle theta is taken to be as a 0, that time the path difference is 0. So the points in the slit being the same phase leads to the maximum brightness. Let f be the focal length of the lens L2 and the distance of the first minimum on either side of the central maximum be x. Then we will have a tan theta is equal to x divided by f. So since the lens L2 is very close to the slit, so we can take as a f is equal to d. That time we will get as a tan theta is equal to x by d. Since theta is very small, so we can take as a tan theta is nearly equal to sin theta. So we have changed the tan theta in terms of a sin theta. So sin theta is equal to x divided by d. Also for a first minimum, we had got that d sin theta is equal to lambda, or sin theta is equal to lambda by d. So from the equations 1 and 2, that is this equation for a minimum, sin theta 1 divided is equal to lambda by d and theta 1 is equal to lambda by d, we will get as x is equal to lambda d divided by d, and this is the distance of first minimum on either side from the central of a central maximum. Width of a central maximum is given by, that is 2 times of x, that is 2x is equal to 2 lambda d divided by d. This is with respect to diffraction of a light due to single slit. This is the difference between interference and diffraction. Next we are having the observing a single slit diffraction pattern. In generally, how to observe the single slit diffraction pattern? That is, the diffraction pattern due to single slit can be seen very easily. That is, an electric lamp with a straight filament under two razors. If we put razor 1 and razor 2 and there is a small gap in between those two, it can be used as a single slit. And the multicolor shown by the CD is because of the diffraction of light. When we see a CD, it is like shining with the multicolors, right? That is due to the diffraction of the light. Next we have a last point, that is validity of ray optics. Also we can call it as a Fresnel's distance. It is defined as the Fresnel distance is defined as the distance of a screen from the slit or aperture when the spreading of light due to diffraction from the center of screen is equal to the size of the slit. This is called as a Fresnel's distance, and this is denoted by the letter ZF. See, the diffraction pattern of a single slit consists of a secondary maxima and secondary minimas which surround the central maximum. So, the spreading of light on the screen depends upon the size of that maximum. So, we know that the angular position of a first minimum on either side of a central maximum is given by, that is sin theta is equal to lambda divided by d, where theta is very small, so we can take as a sin theta is nearly equal to theta. So, we will get theta is equal to lambda divided by d. This is known as a half angular width of a central maxima. See in this, if theta is equal to lambda by d is known as a half angular width of the central maximum. So let d be the distance between screen and the slit. Capital D is the distance between screen and slit. So the linear spread of a central maxima is given by pi 1 is equal to d theta. So we know that theta value, that is lambda by d. So d into theta, that is lambda d by d. When y1 is equal to d, we will get d is equal to d square by lambda. But in this is the least distance through which the light travel before it appreciably bends from the straight line path. This is the least distance through which the light can travel. If we further decrease this distance, so the light cannot travel through this. So that's why this is called as a validity of ray optics. So, and this is known as a Fresnel's distance, that is d is equal to ZF, and we got d as a d square divided by lambda, that is ZF is equal to d square divided by lambda. So we can say that the Fresnel distance depending on the square of the size of the slit and wavelength of the light. And this is the Fresnel's distance or a validity of ray optics.